Hi, welcome to video 19. Today we're going to talk about double displacement reactions, and we're going to emphasize some of the ideas that we introduced in our general reactions video. As you may recall, a double displacement reaction occurs when we have two compounds that are made out of different ions, and we are going to exchange partners in those ions. We're going to have the cations, the positive ions, exchange place, and the anions exchange place to give you two new compounds. Alright, so let's notice how this is in our general sample reaction. I have written the cations, the positive ions, in red and the anions in green. And so you can notice how, in fact, the A is going to push out the C, but the C doesn't just go and float away like in a single displacement reaction and become an element, but the C will come and re-enter a new compound and actually react with B. So in that case, the cations have displaced each other, and so that's why it's called a double displacement, because they go back to make the new compounds. You could think about it being the anions that are doing the exchange, but either way that we look at it, we are going to exchange partners, and we're going to exchange partners in such way that we are always going to make a new compound that has a positive ion and a negative ion in it. You cannot have the two positives together or the two negatives together because they would repel each other. So let's look at a real example. In the case here of sodium iodide, sodium iodide solution reacting with lead 2 nitrate solution, alright, is going to give you two different products. It's going to give you a solution of sodium nitrate, and it's also going to give you lead 2 iodide as a solid. Okay? So first of all, let's look at what's going on in terms of anions and cations. Both the sodium and the lead are cations, and so those are the ones that are going to exchange places. The sodium is going to come in and push the lead out. The lead is going to come in and push the sodium out. Now, notice that the products that we get are not NaNO3 parentheses 2 and PBI. Why? Because sodium has a charge of +1, lead has a charge of +2. So we have to still do our crisscross in order to make the actual products. So the ions that we have are sodium plus and lead 2 plus, and we also have as negative ions the nitrate ion and the iodide ion. Initially, let's see if we can separate those. Initially, the iodide is coming with the sodium, and the lead, there's two nitrates reacting with the lead 2 ion. Well, when we exchange this, we're going to have to do a new crisscross. Sodium and nitrate will react in a 1-to-1 ratio because it's a 1 and 1, so it will make a neutral compound immediately. The lead 2 and the iodide need to crisscross, and in that case the 2 comes down, and that's why we're going to make the PBI2. That's where that 2 is coming from in the I. Once we have done the compounds, then we can go in and actually balance our equation to make sure that we have the right number of each ion everywhere. Alright? So if we had made lead 2 iodide, we had 2 iodides, so we need to make we have to have in the product side, so we needed to have 2 iodides in the reactant side, and that's why the 2 in front of the sodium iodide is present. Alright? Now, you will notice something else about the lead 2 iodide. I have colored it in purple because in order for a double displacement reaction to occur, there must be something that is called a driving force. It is something that will trap the ions so they cannot go back in the reverse direction, And so that driving force is normally the formation either a solid, an insoluble solid, or a liquid. All right? So that traps the ions in the products, and they cannot go back to make the reactants again. Okay? So in this particular case, the lead-2 iodide is the driving force, and remember, we always have to do the crisscross. So how do we do some more of this? Let's look at some other examples. Here we have two other reactions. In one case, we have a solution of barium chloride and of potassium sulfate, and when those react and we do the crisscross, all right, we are going to get, in fact, that we get two potassium chlorides in solution, and then we're going to make this barium sulfate. Barium sulfate is insoluble, and therefore it's the driving force. All right? In the second case, we have lithium hydroxide reacting with hydrochloric acid to give you lithium chloride solution and water. Because water is a liquid compound and it does not break up into its component ions. It does not break up in any significant fashion into H plus and OH minus. It also acts as a driving force. When the driving force makes a solid, all right, that is going to be called a precipitation reaction. That is the type of name that we give it. Precipitation is the name that we say for the action of coming out of solution. When a solid comes out of solution, it precipitates. It settles down to the bottom. All right? If instead we have the reaction like in reaction number 2, where we have a base and an acid. Lithium hydroxide is a base. Hydrochloric acid, of course, is an acid. And they give you as products a salt and some water. That is going to be called a neutralization reaction. So in this case, because we're making water based on an acid and a base, it is going to be called a neutralization reaction. All right? Now, how do we know if what we make is soluble or not in water? Well, we have solubility rules, and although you will not need to memorize the solubility rules, you need to be able to apply them. And the solubility rules are written in such order that if they're further up, they take precedence over the ones that are further down. So, what are those solubility rules? Well, let's look at them together very quickly. First, and this is the most important one, so if all compounds that contain the ammonium ion or that contain alkali metals, i.e. metals from group 1, are going to be soluble. So any sodium salt, any lithium, potassium salts will be soluble. Similarly, rule 2 tells you that all nitrates and acetates are also going to be soluble. So if you have iron 3 nitrate or tin 2 acetate, those will also be soluble. All right? Now, most chlorides, bromides, and iodides are soluble, except those that are combined with silver, lead, or mercury 1. Similarly, most sulfates are going to be soluble, except those of silver, lead, mercury 1, barium, strontium, and calcium. So basically, most of the sulfates of group 2 are insoluble. All right, so that is important to know. Now we're going to be looking at the ones that are normally insoluble. Carbonates, sulfites, phosphates are normally insoluble. But of course, we know that rule 1 tells us that anything that has ammonium or alkali metal is going to be soluble. So those, of course, are an exception to the fact that carbonates and sulfites and phosphates are insoluble. Those will be soluble. Hydroxides are going to be insoluble. Again, except for those of ammonium, of group 1, and those of barium. All right, so the hydroxide of barium is actually going to be reasonably soluble. The other ones, not so much. All right. Sulfides are insoluble, again, except for those of alkali metals, ammonium, and in this case, those of group 2. The sulfides of group 2 are also soluble. And then oxides are insoluble except for those of calcium, barium, and the alkali metals. All right? So that's the basic idea. So let's try applying some of those rules to some sample questions. So on top, I've put 3 sample questions, and then I've given you 4 to try at home to complete for a class. Okay, so we're going to go ahead and work on these ones. If we look at the first one, we have silver acetate, and we got calcium bromide. And so those are the ones that are going to exchange place. The other ions are going to be the acetate ion and the bromide ion. So let's write the ions, the positive ions that we have. Ag plus. We also have Ca2 plus. As negative ions, we have CH3COO negative, which is the acetate ion, and we have Br minus. Notice that I'm not putting the 2 there because the ion is Br minus. There happens to be 2 of them. We'll do the balancing afterwards, once we have the compounds. First, we want to make the exchange. So we're going to go ahead and exchange, and we're going to do the crisscross for each one of them. One comes down, one comes down. So the compound here would be AgBr. And the 2 comes down, the 1 comes down. This would make calcium, in parentheses, acetate. And so now we need to know which one's soluble and which one is not insoluble. Sorry, which one's soluble and which one's insoluble. Because something has to be the driving force. Otherwise, we say no net reaction occurs because the reaction can go back and forth all the time. And so there's no way of locking the products. All right? So if we look at the rules, and you have them in the sheet that I gave you already in class. All right? So we can check, oh look, calcium, well calcium could be soluble or insoluble, we don't know, but there's the acetate ion. And the second rule tells us that all acetate salts are soluble. So we're going to say that this is AQ. Now, the third rule says that most bromides are soluble, except those for silver. This happens to be the bromide for silver. So we're going to notice, oh, so this is going to be insoluble, and this is going to be our driving force. And it's good to identify the driving force. It's a good practice to have because that will tell you whether you are sure that you made something or not. All right? Now let's look at the second one. We've got, sorry, is it balanced? Before I forget, is it balanced, the reaction that we just did? Well, we have 1 silver and 1 silver. We have 1 acetate and 2 acetates, so I'm going to need a 2 over here. Now I have 2 silvers on this side, so I'm going to need 2 silvers over here. All right, that seems to be balanced now. But now I have 2 bromides, 1 calcium, 1 calcium. Now we're all settled and balanced. Okay, let's try the second reaction. Nitric acid and aluminum hydroxide. All right, so what are the ions that we actually have? Let's see. All right. The positive ions are going to be H plus, that is coming and separating from the nitric acid, and we're going to have aluminum 3 plus, which is trapped in the hydroxide solid. Okay? Now, the counter ions, the negative ions, the anions, are going to be the nitrate ion, again, that is coming from the breaking up of nitric acid, and we're going to have 3 hydroxide ions that are floating around. Again, those will be able to exchange once the reaction takes place. If we move those around, what do we make? Well, H and OH react together to make H2O. All right? That's the exchange. We could write it as HOH. It's the same thing. It's just kind of a weird way of writing water if we can just write it in a more simplified fashion. All right? Similarly, when we do the crisscross, all right, this 3 comes down, this one goes down, and so we're going to get that we're going to make aluminum nitrate. And aluminum nitrate, we need to have 3 of the nitrate units in there. We are not going to change that 3 that is in the nitrate itself. We're going to put another 3 outside to say that we have 3 of those ion units. Okay? And now we check. Well, the second rule tells us that all nitrates are soluble, so we know that aluminum nitrate is going to be soluble. And how about water? Well, water is a liquid. Water is soluble, but it's a liquid. And that's the key here. We have made water. And so water is the driving force of this reaction, because this is a neutralization reaction. We have reacted an acid with a base and made water and some type of salt. All right? Now, the next reaction is a little bit special because it's also a neutralization reaction. So you know that we're going to make some water. All right? But it's actually a little bit different. So let's check that out. When we have sulfuric acid reacting with sodium carbonate, this is initially what are the ions that we have in there. All right? We're going to have the H plus ion. Oh, sorry. Before I go into that, let me not forget that I did not balance the one on top. So let's check for balancing. I've got aluminum, and I have 3 nitrates. All right? The nitrates are coming from here. There's only 1 nitrate here, so if I put 3, I now have 3 nitrates. This has 3 plus 3, 6 hydrogens. I have 2 hydrogens here. If I put a 3 there, I think we are now completely balanced. We can check by checking the aluminums and the oxygens. We've got 9 plus 3, 12 oxygens. 3 plus 9 is 12 oxygens. We've got 1 aluminum. And so we are balanced. All right. So back to the other reaction very quickly. Sulfuric acid and sodium carbonate. The positive ions are going to be H plus and Na plus, and the negative ions will be the SO4 2 minus from the sulfuric acid and our well-known anion, the carbonate ion. So we're going to exchange those, and initially it makes these 2 compounds. The first compound that we can see that it can make, if we do the crisscross, the 2 comes down, the 1 comes here, is going to make sodium sulfate, and it theoretically would make, if we actually do the second crisscross, it theoretically would make, and I'm just going to write it here in black, all right? H2CO3, carbonic acid. But carbonic acid is very, very unstable. So it does not stay like that. Instead, carbonic acid breaks up into water and carbon dioxide. And that's whenever you put acid on a carbonate or in a bicarbonate like baking soda, it is going to fizz because it's producing carbon dioxide. All right? So the products in here will in fact be water and carbon dioxide. All right? This never really is the product of the reaction because it breaks down. It is too unstable to stay around. All right? And so let's check which things are soluble, which things are insoluble. Well, we know that all salts of sodium are soluble, so that's going to be AQ. Water is a liquid, and in fact carbon dioxide is a gas. This is still going to be our driving force, all right, the fact that we made that liquid, and so that is going to be the driving force for the reaction. Is it balanced? In this particular case, it is. All right? So, at home, attempt the following 4 questions. All right? Now you can see them a little bit better. And please try to underline and to identify which one is the driving force for each one of those reactions. All right? Have a great weekend. Have a great rest of the week. And I'll see you in class. All right? Great. Bye-bye.